In this video, we will discuss special kinds of thermodynamic processes. The first type we will discuss are adiabatic processes. Adiabatic processes are processes during which there are no heat transfer. It can be because of very good thermal insulation or because the process is too quick for heat transfer to happen. In this case, Q will be equal to 0, and since delta U is Q minus W, then delta U is equal to minus W. For a gas expansion, we have seen that the work is positive. And so for an adiabatic expansion, then you can conclude that delta U is negative. And since we know that for an ideal gas, the internal energy only depends on temperature, it means that the temperature decreases. Now in this demo, I will do an adiabatic expansion with a canister of air duster. I put a thermometer on the back of the canister. It is attached with a piece of tape and it measures the temperature. You can see the temperature in Celsius on the display. And now I will simply release the gas. As the gas is released, it expands. And this is happening so fast that there is no time for heat transfer. And we can consider this as an adiabatic expansion. And you can see that the temperature is dropping. We are now below the freezing temperature. Now let's see how low it can go. This is really cold now. As you can imagine, we will also learn this in the next chapter. Engineers will use that kind of adiabatic expansion to make refrigerators, for example. Another example of an adiabatic expansion, which will decrease the temperature, is when you open a bottle of champagne. The gas expands rapidly, so there is no time for heat transfer, and the temperature of the gas decreases. And this produces condensation, which will make a white cloud when you open the bottle. Another example is what is called carburetor icing. The carburetor is a device that blends air and fuel for an internal combustion engine. The air flows through a small aperture and then expands. So we have an adiabatic expansion. And air can be cooled below the freezing temperature and ice can form even if the outside temperature is well above freezing. And so if you fly such a plane, you need to check the humidity level, the temperature, and the airflow, because you don't want the carburetor icing and then it blocks the engine and you could run out of fuel. Another example, if you're a paraglider or a pilot of radio-controlled airplane, you're looking for thermals. Thermals are bubbles or columns of hot air going upward. If you're looking for thermals, it is a good idea to look for areas with dark surfaces. Why is that? Well, remember that a good absorber is a good emitter. So the dark areas, such as a plowed field or a city, have an emissivity closer to 1. And so there will be a decent amount of heat radiated. Another indication is if there is a cloud above this area. This is a good indication that there might be a thermal. Right. The reason is because of the radiation, the air above the dark area is warm. If the air is warm, it expands. If it expands, it becomes less dense, and so it will rise up. And as it is rising up, the surrounding pressure decreases with altitude, and so it will rise even faster. And since it is rising faster, then there is no time for heat exchange, and air is a poor thermal conductor, and so this is like an adiabatic expansion. And the temperature will decrease, and water will condense, forming a cumulus cloud. Now let's come back to the adiabatic process. As you can imagine, if the temperature decreases for an adiabatic expansion, then it will increase for an adiabatic compression. Right? This is because for a compression, the work done by the gas will be negative. And so for an adiabatic compression, delta U will be positive. And since for an ideal gas, the internal energy only depends on the temperature, then the temperature will increase. An example of this is if you inflate your tires with an air compressor. You may have noticed that the air is warm. And this is because the compression is happening quite fast, so there is no time for heat transfer, and this is almost an adiabatic process, and so the temperature of the gas increases. I'm going to illustrate that the temperature increase during an adiabatic compression by burning a little piece of cotton. So I'm selecting a small amount of cotton, and then I insert the cotton into a tube. The tube is full of air, and I will use a piston to do a rapid compression. Now I will turn off the light so that we can see the cotton burning. It will be easier to see in the dark. Okay, so now I will push the piston really quickly. Ready? Now let's watch this in slow motion again. The temperature increases so fast and so much that it becomes above the flash point of cotton, and it burns instantaneously. Okay, another type of process we will discuss are the isochoric processes. An isochoric process is a process that happens with a constant volume. And so on a PV diagram, you can represent this by a vertical line at constant volume, going up if the pressure increases, or going down if the pressure decreases. And in both cases, you see that the work is equal to 0. And so since delta U is Q minus W, it becomes delta U equal Q. And this process does not do any work, and all of the heat is absorbed into internal energy. Another type of process is the isobaric process. This is a process during which the pressure is constant. On a PV diagram, it would be represented by a horizontal line at constant pressure, and the work is represented by the area below the curve. So it is a rectangle, which is easy to calculate. And we take this as a positive if the volume increases, and a negative if the volume decreases. In fact, the formula for the work is that the work is equal to P times V final minus V initial. Now, remember that we already discussed an example of an isobaric process when considering the boiling of water at ambient pressure, for example. Finally, one more special kind of thermodynamic processes are the isothermal processes. Those are processes for which the temperature is constant during the entire process. So remember that for an ideal gas, the internal energy only depends on the temperature. So if the temperature does not change, then the internal energy does not change, and delta U is equal to 0. So all of the heat is converted into work. And we have already seen in a previous video that for ideal gases, the pressure is given by nRT over V. So you can represent an isothermal process with the inverse volume curve on a PV diagram. And we have seen that the work is given by the integral of P dV, which gives you nRT log of V final over V initial, and this is also equal to nRT log of P initial over P final. Now, let's summarize all the special processes on a PV diagram. We can draw a few curves at constant temperature, and we call those isotherms. And let's consider a starting point. So for an isothermal process, it will follow one of the isotherms. For an isobaric process, we have a constant pressure. For an isochoric process, we have a constant volume. And for an adiabatic expansion, the temperature will decrease, so we arrive on a lower isotherm. This kind of diagram is very useful because remember, you can use this to calculate the work done by the gas. Right? By taking the area below the curve, it gives you the work done by the gas. Now let's keep drawing. Let's say that you prepared cookies. Right? You just took them out of the oven and put them in a jar. Then you place a lid on the jar, but the lid is loose, and so it is not airtight. And let's consider the air inside the jar. As the cookies cool down, the air will cool down. But what kind of thermodynamic process happens to the air inside as it is cooling? Right, during this process, the heat goes out, right? So it is not adiabatic. The volume of air decreases, so it is not isochoric. It is open to air, so the pressure is constant, so it is isobaric. And the temperature decreases, so it is not isothermal.